they found that if you implant to saturation at low temperatures, the key being there that the deuterium diffusivity is very small, so it isn't mobile once you inject it into the lattice, that one reaches atom ratios of about 1.3 to 1. So our experiment then basically consisted of performing low temperature implantations to achieve these high stoichiometries, and then using a charged particle detector to look for the energetic particles from DD nuclear reactions. Of course, as has been apparent from this conference, when one uses high pressure gas phase charging or electrochemical charging, these higher atomic ratios, in particular atom ratios above 1, are not easily achieved as they are with the implantation. Our experiment is outlined here at the bottom. We began by ion implanting 10 kilovolt deuterium from an ion accelerator into palladium, with the specimen being held either at 40 or 80 Kelvin. The implantation was carried to the point of saturation. During the implantation process, we monitored the buildup of deuterium within the metal matrix by actually using that charged particle detection system to observe both energetic protons and tritons from the D-on-D reaction. I stress that here we're speaking of the reaction being induced by the incident ion beam itself. After the condition of saturation had been realized at these low temperatures, the ion beam was turned off, and this charged particle detection system was then used to look for the 3 MeV protons, or in fact any energetic charged particles from DD nuclear reactions in the absence of the ion beam. Just to illustrate the kind of information that comes from the charged particle detection system, what we have here is the output of a multi-channel analyzer, which basically gives the number of particles into various bins as an increasing channel number corresponds to increasing energy. This is actually a spectrum that was obtained during the implantation process. So the energetic D from the beam hitting D in the target produces the energetic tritons here at lower energies and the more energetic protons. For those familiar with these things, I will mention that we had a 2.5 micron nickel foil in front of the detector, which serves to range out all of the lower energy charged particles that are of no interest. But the 1 MeV and 3 MeV particles are readily apparent. I would also mention that this is only a portion of the spectrum. In fact, we detected out to something like 10 MeV particles, but I've just shown you the portion where we actually saw energetic particles coming out. Well, the buildup of deuterium at low temperatures during the implantation process, in this case at 40 Kelvin, is shown here. What I'm on the horizontal axis, I have plotted the incident fluence of 10 kilovolt deuterium going into the palladium, and this then is the nuclear reaction yield. The energetic particles produced by the high energy deuterons, striking deuterons already within the material. And the key point to be made is that initially we have a more or less linear buildup, which then progressively saturates as one reaches the saturation concentration. Again, a key motivation here is that we're seeking deuterium to palladium atom ratios above 1. We wanted to see whether that has real importance in this search for cold fusion. So a key question is, have we actually realized this superstoichiometric condition? And I'd like to point, before giving you the results, I'd like to suggest 3 indications that we have. The first indication, of course, is that we have reproduced the implantation conditions of about a decade ago, when very detailed profiling measurements did indicate that when you implant to saturation at such temperatures, you achieve an atom ratio of 1.3 deuterons per palladium. Another indication is that we're monitoring this build-up in saturation through the nuclear reaction, and we thereby have information on the concentration. And one can, in fact, model this in some detail and thereby establish reasonably well what the concentration is. In the model calculation, the key inputs are the depth distribution of the implanted deuterium, the deposition profile, as it were, and that can be rather reliably calculated using Monte Carlo methods. There's a generally accepted code called TRIM, which was used. So this is the depth profile of the implanted, the deposition profile of the implanted deuterium. The other key input is the nuclear reaction cross-section as a function of depth, because that essentially establishes the sensitivity with which that nuclear reaction is monitoring the concentration buildup. Well, at these energies, the DD cross-section is well established, and also the stopping rate, or the energy loss within the matrix, and so this then is a net result. This is how the DD cross-section varies within the target when you're bombarding with 10 kilovolt deuterium. So you can see we're primarily sensing the near surface region here. When you then put this into a model calculation, you can actually model the buildup of the concentration profile. This is deuterium to palladium atom ratio as a function of depth. And in this particular calculation, we assumed, for sake of comparison with the data, we assumed saturation at 1.3. And so you build up and then achieve this kind of saturation. Well, when you do the calculation, you come up with the curved line here, again assuming 1.3 saturation, and it appears to be rather consistent with, in fact, it is a rather clear indication, we think, that we are saturating around 1.3 deuterons per palladium in the near surface region. The third indication, before getting to the results, the third indication I would present that we are actually supersaturating the lattice is that we have examined the release of this implanted deuterium from the palladium as the temperature is increased. In particular, in the experiment that I'm representing here, we went to low temperatures, implanted to saturation, and then instead of turning off the beam and looking for cold fusion, in this particular case, we continued to bombard with energetic deuterons and increase the temperature at about 2 Kelvin per minute, and then the idea being to see where the deuterium comes out. Now, if at deuterium to palladium ratios less than 1, where you have the well-established conventional diffusion, you in fact expect to see release from the specimen out in this range of 200 Kelvin, and in fact we do see a large release stage out here. However, totally unexpected for compositions below 1 is this rather sharp and well-defined stage down at about 120 Kelvin. Well, I think that suggests an obvious interpretation that we're losing the superstoichiometry in this stage, and in fact you see that we do in fact pop down to a composition more or less conforming to those that we have heard discussed so much this week. Why would the excess diffuse more rapidly? The notion, the energetics of this kind of system were discussed by Pete Richards earlier this week. The essence of it is that in the normal deuteride with the octahedral sites not fully populated, the octahedral solution sites, you have diffusion, thermally activated diffusion, in which you hop from that site over a saddle point to the tetrahedral site and then to another octahedral site. If, however, the octahedral sites are filled, the excess deuterium cannot drop into such low energy sites, and therefore the activation energy to get over the saddle point is less. And this is a diagram calculation due to Pete Richards, where we're illustrating that the dashed line is at the normal composition, and you sit in equilibrium in the octahedral site. You rise to diffuse, you rise over a saddle point into a tetrahedral site, and then over another into another octahedral site, and so on. But if you have excess, it goes into the tetrahedral site, according to calculations. There is a repulsion between hydrogen in the tetrahedral and octahedral sites. So the bottom line is the hydrogen sitting in the octahedral site, due to the repulsion of neighbors, now has higher energy. So it can more easily diffuse. It does not have to go as far to get over a saddle point. So the diffusion activation energy is reduced. You diffuse at lower temperatures. And in fact, calculations by Richards, preliminary calculations I should say, suggest that the separation in temperature between this stage and this is semi-quantitatively consistent with what we see. So all of these indications are basically going to make the point that we believe we do have a palladium matrix in which all of the octahedral sites are essentially filled, and we have superstoichiometry, about a 30% excess in the lattice. And then the question is, does that have any influence on cold fusion? And I'll say immediately that we, in fact, were not able to detect any evidence of cold fusion occurring in our materials after the ion beam was turned off. The upper portion of this view graph gives some of the relevant conditions. This is 397 palladium. We investigated two conditions: cold rolled material, and then material which was annealed at 1,000 degrees under a high vacuum. The deuterium to palladium atom ratio, as I indicated, 1.3. The amount retained in the material is about 10 to the 18 per square centimeter. 2 minutes. Thank you. And this is the detector solid angle. There are three experiments represented here. In one case, we implanted the saturation at 40 Kelvin, and then we remained at that temperature with the charged particle detector running, no beam on the sample. During this time, in the detection system, we got one count. Our detection system does have some background, and which is indicated in parenthesis there. And since that is a